Hello. Yeah. I think we can start. Welcome everyone to a post-lunch session of this conference now. And this session is about late universe, dark matter. And the first talk will be given by Gaurav Goswami on self-coupling of light spinless dark matter and its astrophysical observations.
I'll just check. Okay. So let me begin by thanking the organizers for inviting me and for allowing me to present my work. So I think this session has lots of talks about very realistic stuff. This is slightly more speculative than the other talks in this session, but I guess yeah. So towards the end I'll get to something more realistic, but yeah, to begin with I'll talk about something far more basic. So I'll make some remarks on dark matter because we had some discussions the last couple of days, and then some remarks on what is called wave dark matter. Then I'll talk a little bit about its couplings and about the kind of configurations that we are interested in and how that connects to actual observations and things like that. So let's begin with this. So I think this is probably not a controversial thing to say that there are observations at various length scales which can be interpreted to be evidence in favor of existence of dark matter. And there are of course other reasons which I won't get into to suspect that okay, this cannot be this dark matter cannot be made of particles in the standard model of elementary particle physics, and so that's why there could be new elementary particles which are yet to be discovered. And what that means is, so if there is, what are the properties that elementary particles have? So they, for example, have a mass. So we can have this question about dark matter itself. Okay, what is if there is even, of course, it could be lots of new particles, but even the simplest scenario where there is only one new particle, what is its mass? What is its intrinsic spin? What is its representation in, let's say, the internal symmetry group of standard model? Right? What are the couplings to standard model particles? Right? What are the So, and things like that. So of course there are various models of dark matter that people write down, but these are the questions that one has to answer. And the important thing is this, that since gravity is universal, dark matter has gravitational interactions, and there are many experiments which are designed to detect dark matter. All of them rely on the existence of some non-gravitational interaction of dark matter, and the fact that we don't detect dark matter just ends up imposing constraints on, or let's say upper limits on, these couplings of dark matter to standard model particles. So that's the way this game is usually played. Okay, so that's the first thing which I wanted to say, which everybody I guess knows. Now the second point is about a specific kind of dark matter, which is wave dark matter, which is again the important point is this, that if I have a gravitationally bound system of some size, let's say r, and some mass m, and let's say it consists of identical particles, then if these particles are fermions of mass small m, then Pauli's exclusion principle can be used to argue that since if I want the Fermi velocity to be less than escape velocity, then there is going to be a lower limit on this mass of this particle. That means if I do know that there is a system like this which exists, and if I know that it's going to consist of identical fermions, then mass better be bigger than this value. So for example, if there are dwarf galaxies, this will turn out to be something like 100 electron volts. What that means is if dark matter particle mass is less than this, it is going to be boson, right? So that's one of the important things to understand. So boson means okay, it can have of course spin which will be an integer spin, so it could be any of that. Okay. The other thing is for bosons, one thing which is possible is that if you have a system of identical bosons, and suppose, it's possible for the mean occupation number to become large as compared to 1, that's possible, and in that limit this system behaves like a classical wave. That's the way we understand electromagnetic waves in terms of, if fundamental degrees of freedom are photons, then this is the way it works out. And so again, using this requirement that mean occupation number should be large, we know that the particle mass should be less than this. Of course, meaning if we are talking about this kind of regime, then the individual particle mass better be less than 30 electron volts, and in that case it will show wave-like behavior. So that's another bit about, again, this is a specific kind of dark matter that we are looking at. And so the picture that we have is, instead of Earth being bombarded with a lot of these particles, it's going to be surrounded with waves, and this is the kind of picture of dark matter that we have. And of course we still have to ask similar questions. Now again, as I said, this could work for any boson of any spin, but the simplest possibility is to work with spin 0. So that's the one that we are going to be examining in this talk. Now there are various ways of imposing constraints on other properties of this. So for example, there is a particular way in which something like this is produced in the early universe, which is called misalignment mechanism, which I won't have any time to get into. But from that we know that the mass of this particle mass is going to be greater than, let's say, Hubble parameter at the epoch of radiation matter equality, which is around this. And another is, okay, if I have again another bound system of some mass m, size r, and since you'll have, if suppose something has very small mass, then even this uncertainty principle is going to be an important point. So because of that, if I want the corresponding velocity, which is the result of this uncertainty principle, is going to be, let's say, smaller than the escape velocity, then this will give you another lower limit like this. And so that is one way one could motivate a mass value like this. I am not necessarily getting into small scale structure problem or something. Even from basic physics, this is a number which is interesting. And so this is what I will be calling ultralight dark matter. Okay, so that's the second point. So that's why what we are dealing with is, so this is the entire range of masses, but we are dealing with this range, let's say, and we are talking about intrinsic spin being 0, and we are interested, then the next question is, okay, what are the couplings of these particles? That's the question which we have to ask. So we get to that. So if it's just a spin 0, right? So these are the kind of things I can write down. In fact, I have written this assuming something like, you know, that this scalar is, let's say, a standard model gauge singlet and things like that. But these are basically terms which are, so these are the possible higher dimensional operators which exist with, some kind of interaction exists with, let's say, photons and gluons and electrons and things which still survive the universe at late times. And so these parameters, d gamma, dg, all of these things, they can be constrained by experiments. So for example, there are various ways of doing that. So because stellar cooling, or the fact that this would mediate forces, or time variation of fundamental constants, all of that is going to can be used to impose constraints on these numbers. So that's something which is possible. And I have already said something about this m. The only thing left in these equations is this lambda, which is what I am going to get to. So the important thing is this. So there are observational upper limits for all of these couplings, and that just shows that the coupling to standard model is really small. Then the only things left over are these things, right? These are the leading terms. And then so when people talk about something called fuzzy dark matter, they basically ignore this term completely, and they focus all their attention on this m, and they try to find out ways of let's say ruling out or constraining the possibility that mass of the dark matter could be whatever I am dealing with, let's say 10 to the minus 20 electron volt or close to that. And then of course this is something which is completely ignored. And an important question to ask is what exactly is the value of lambda, which can be probed experimentally and which can be tested, right? And if we can ignore it, but then one has to ask whether one can really ignore it given the observations. And so that's why whether self interactions of like dark matter, whether they can have observable implications or not, that's an interesting question to ask. So an example that we would keep in mind is that of an axion. So again, an ultralight axion. So again, we don't have to know anything else here. The only thing is, for that ultralight axion, there are ways of arguing, and maybe I'll just skip the details here. And that will tell us that this lambda actually could be really small. Again, that's a model dependent question, but it could be a ridiculously small number, something like this, of this order, 10 to the minus 96. And one might think that, okay, fine, if something that small is involved, then there is no reason why we should be worrying about it. But so basically, if you are talking about mass which is like this, and a self coupling which is this small, and of course if I tell this to a particle theorist, then they'll get uncomfortable, because they'll be worried about whether unknown short distance physics could ruin the potential of this kind of scalar. but this talk is not about those issues, those model building issues. So that's why we'll be interested, okay, whether observationally you can impose any constraints on this. So in particular, we are interested in what happens on galactic scales, let's say, and whether some observations on those scales can be used. Okay. So one important point that I should make is this, that so this is the kind of scalar that we are dealing with, but since it's going to actually oscillate at the bottom of its potential really rapidly, when I say that dark matter is not realistic, in this context what it means is this, if I write this phi in this form, then this psi is a very slowly varying quantity. I mean, and so that's why our usual Klein-Gordon-Einstein equations are going to reduce to Schrodinger-Poisson equations. So that's the kind of thing that we have to really deal with. Okay, so this is the kind of equation one has to deal with. So there will be some effect of course there will be gravity, so that's why there will be some effect of gravity. If I'm since I'm including the self-interaction terms, there will be this, and of course there will be, even in quantum mechanics we know that wave function, for example, spreads, right? So basically that's what going to be controlled by this. So there are going to be all of these terms which are going to control the dynamics of this system. And given this equation, for example, one could ask, okay, what are the values of lambda that one could probe? So if I have a system of mass m, size L, and the kind of system that I'm interested in, something which is going to be the, let's say the core of a dark matter halo. So there, this lambda that you can probe actually will turn out to be also a really small number. So not only theoretically we have numbers which are this small, like for lambda, even observationally you may end up constraining numbers which are this small, and this is just a comparison with another number which is very famous. The corresponding lambda will turn out to be small, but that's not that important. So the important thing is it is possible to probe something which is this small, and so that's why we get into this kind of self-gravitating scalar field configurations. So basically what we were doing in the last few years is we were looking at some solutions of these equations which have some properties, like in some of the studies we were basically looking at solutions which have these properties, and in some others these, and basically using that we ended up imposing some constraint on lambda. Of course, so this is Behag who spoke yesterday. So basically he was the one who led these studies. So that's the that's the machinery that is useful in doing this. So yeah, now let's proceed. So what could happen is that if you write down solutions of these equations which are going to be, let's say, which are going to have these properties, which are going to be spherically symmetric and which are going to be localized and stationary. So those solutions could be, I mean, sometimes people just call them solitons, could have this kind of, let's say, could be some spherical system like this, spherical symmetric system. So gravity is going to squeeze it in. There will be gradient term that I told you, which is going to basically expand it, and then depending on whether this lambda is positive or negative, there could be basically it could either support gravity or oppose gravity, and so depending on how much lambda is there, the density profile is going to be different. So this is going to be, so this is the kind of solution one can study using this, and there are different kinds of solutions one can obtain. Let me just skip this because there are, as I said, other talks in this session which are going to be our observations. So in this context, one can find out various ways of imposing constraints on m and lambda, and these are some of the things that we did recently. So since I have very limited time, I'll just very quickly talk about this. So the important thing is this. So we have the dark matter halos, and we have cores of dark matter halos which can be modeled with this kind of wave dark matter and this kind of solution that we are talking about. And for that, I mean, one has to solve these Gauss-Pitowski-Poisson equations, which are the Schrodinger-Poisson equations with this lambda phi 4 kind of term, or phi cube in this case. And there is going to be these tunable parameters, that of course the mass of this particle can be adjusted and the value of this self-coupling can be adjusted, and of course how many, let's say, initial particles you use to form this system. That it's, even though m and lambda will be the same for every system in the universe, this will not be the same, right? So there could be some systems which have more particles, some which have less particles, and that is parameterized by this scaling parameter S. And so these are the parameters one can tune, and based on that, something observable can get affected, like for example the density profile of this, and that will eventually affect affect the rotation curves and things like that. and similarly so basically things like that. So that can be done. So for instance here, and this was some, for example, it's possible to impose constraint on in this m lambda plane using let's say observational upper limit on the mass within some fixed distance of the center of a galaxy, for example. Okay, and suppose we know that, then there could be some constraint on, okay, how much m and what value of m and what value of lambda is allowed and what is not allowed and what can be probed. So I mean there are details of this which I am going to skip for now, and depending on whether your lambda is positive or negative, so there are various possibilities here. And similarly, one of the things which happened recently is that people were claiming that even if rotation curves are satisfied by this kind of dark matter, what is called fuzzy dark matter, which has non-zero self interactions. So even if it satisfies this kind of rotation curve, it will end up not satisfying some kind of umbilical correlation which was between soliton mass and halo mass, and so because of that, so which was found out from simulation. So there was a claim that, okay, maybe this kind of thing will not work for, so basically this was a way to rule out fuzzy dark matter. The important thing is if you include this very small lambda, very small value of self interaction, in fact you, of course this kind of soliton-halo relation is going to change because the presence of this kind of coupling is going to change the relation a little bit. But the important thing is the argument by which you rule out fuzzy dark matter, that will no longer be true, and so because of that, in fact, one can impose some constraint on lambda, how much of self-coupling should be there if you want to satisfy not only rotation curves but also this kind of soliton-halo relation. So that's another thing which is possible, and again the lambda that you have to deal with, you need is something which is basically pretty small. Okay, and since I'm running out of time, I'll just mention one more thing, that okay, you could you could have, let's say, a central galaxy and there could be a satellite galaxy, and the effective potential that, let's say, dark matter feels in this satellite galaxy, because it's in this rotating system, it will have this kind of tidal potential. So basically this would be the potential energy in the absence of this kind of tidal effect, but in its presence it's going to be like this. So if it's particle-like dark matter, it will just stay here, but if it's wave-like, it can actually tunnel out. And so there was an argument that, okay, if it is wave-like, then basically there is no way many of these satellite galaxies could survive for cosmological timescales. But on the other hand, again, depending on how much lambda is allowed and whether it's attractive or repulsive, they could survive on cosmological timescale. So that's another thing that we explored. So let me skip this. So here's the main point that I wanted to make, that so we are not really concerned about a specific model of some ultralight dark matter, but the important thing is even very tiny self interactions can have interesting implications, especially at astrophysical scales and on things that we are dealing with. It also sometimes in some cases evades the constraints on fuzzy dark matter, like we keep on hearing that it's ruled out, but usually it's also assumed that somehow it has absolutely no interaction, and when they say absolutely no interactions, what it means is it's small even as compared to this, so which is also possible, but the point is one has to understand what are the assumptions which have gone into it. So the important point is this, that while discussing ultralight dark matter, it's kind of important to not ignore this kind of self-coupling. So that's the punchline, I guess. Thank you.
Thank you. Questions? Arka?
Out of
yes. Good.
Just out of curiosity, so since you mentioned lambda offered at 10 minus 92, so quite small, so the interaction strength for this kind of coupling, is it weaker than gravitational strength of interactions of lambda, because the mass is also extremely small,
right.
so that do you have any
yeah, so there is so this is close to that, basically there is an argument for what will be the let's say weak gravity conjecture constraint on fuzzy dark matter. So there is some work like that. This is like very close to that limit when it can get weaker in gravity, but this is not probably, this is probably fine, this is probably still going to be okay. But yeah, in fact for ultralight axions, where for m 10 to the minus 22 electron volts, lambda value 10 to the minus 96, it will be in the problematic regime from the point of view of weak gravity conjecture. Yes.
Yeah, please go.
So I missed the point about the tunneling. So there's I don't know if you're talking about the same effect, but there's a very simple effect which we looked at, which is just whether these things will survive or not. Subhalos falling into host halos will survive or not, just from the tidal interactions. Is this tunneling the same thing, or are you talking about something else?
So when you say whether it will survive or not, so
In the presence of these self-interactions, so we
Yeah.
looked into this.
yes, yes.
So are you doing the same thing, or
Yeah,
is the
it's-
tunneling
it's-
something else?
No, no, yeah. So I think it's just going to be called tunneling because now this is a wave. That's, I think in terms of effective potential, that's the way you'll describe it, but it's the same effect that you have studied, yes.
Ranjan.
Thanks, Gaurav, for the excellent talk. I mean, when you do this survival thing, we are using Fornex, so is dynamical friction important?
Dynamical friction,
Whether-
I don't know whether it's important, okay. I mean, we have not looked into that, yes.
Okay, okay.
So I have a comment and a question. I don't know if there will be time for questions. So my comment just on something you mentioned in the second slide, that dark matters could be evidence for physics beyond the standard model. There's actually one counter example, one candidate given by Glenn Starkman and Case West and colleagues, just what they call macro dark matter, which is QCD strange quark nuggets. So strictly speaking, that's still,
So we
that's
don't know
still,
that quark nuggets, but we want us to establish that quark nuggets exist in standard.
so yeah, but still astrophysically
If
that's
you
not,
can't talk to a
they are not
lattice
ruled.
QCD guy, they should show that it exists.
Oh, so you disagree? Okay. Okay, good.
But
Okay,
we'll
so I-
discuss that.
Okay, but anyway, can I ask one more question? Okay, fine.
Running out of time. Sriram, if you have a quick question, in the meantime you can set it up.
What do you mean by that? Of course, I mean, it's just the usual scalar field, right? I mean, what is the, I mean,
I'm not sure you will arrive at those equations with dynamical fixed in a non-realistic
you will arrive at Schrödinger-Poisson equations? Yeah, you arrive, you basically take the non-physical limit of,
Get I dCf by dt.
so basically so yeah, so basically if you start with your usual Klein-Gordon-Einstein equations, or, I mean, if you want to start the action, you can start the action, and you, see, this is the field that we are dealing with now, this is the slowly varying field. And for the distribution, in fact, the way we derive Schrödinger equation from Klein-Gordon equation in general in a textbook, so this is basically just that, just the same argument. Okay, you're not convinced, I'll talk to you.
Okay, let's thank Gaurav again. Yeah. So, next talk is by Subha Mujumdar from TIFR Mumbai, and he's going to take us back to 40 years back for Halo mass structure.
Hello. Hello. 12th minute. Okay. Okay. So I should start by thanking the organizer, especially Dheeraj, for making it possible to come back to IIT, not IIT, IMSC after 26 years. So I was here in 1999, that also to visit a friend, and I've never been to IMSC. So this is an opportunity. Thank you. So I'm going to talk about dark matter halo structure around real observed galaxies, and there will be a series of talks after me. So I will make things a bit, sort of build up the story, and some of these first slides can probably be used for the others. So this is a work which was done not by me, but mainly by my former student Manush Manju, who is in New York University right now. And so over here you can see basically these are the same galaxy. This is NGC 6946, it's from the SPARC survey. It's in optical and IR. This is observed, and we know these galaxies exist. The circles around this is supposedly the dark matter halo that we don't know. Probably that it's even larger than this. And of course, what we want to understand is basically, what we understand of dark matter from observation is basically about everything over here, but looking at stuff that's inside, or wherever, I mean, looking at visible stuff. And we have to see how these things are pans out. So this is my plan of my talk. I'm very proud of this. This is the first time I've used ChatGPT to make me a figure. And it tells me that 10% will be for motivation, 50% will be the last 40 years, and then another 40% will be what has happened in the last 1 year or 2 years, basically. Okay. Yeah. big improvement. Okay. So let's start, dark matter halos. So why do dark matter halos? Dark matter halos are the building blocks of all large scale structure. Milky Way, we live inside a dark matter halo. All galaxies are inside dark matter halos. In fact, one can postulate that all matter are inside some dark matter halo or other if you make the halo smaller and smaller. This is the halo model of large scale structure. And people sort of know the first thing about it, have this many, many times, that if you look at the density of these dark matter halos, this is a self-similar formula, universality there, irrespective of the fact that there is hierarchical structure formation, things fall in or accrete, you have a universality in the dark matter density profile, which goes with an NFW profile. There can be some other profile also, but more or less the same profile basically agrees with all dark matter halos in simulations. Okay. Similar universality is there in velocity also. So if you look at the distribution function of velocities, it is seen from simulations that, for example, some done by Mao et al., that over there also there is a universal profile. So there is some scale factor over there. So the universal fitting formula is there. It depends primarily on R by Rs. So this one depended on R by Rs, except over here there is an additional shape parameter. So every R by Rs, there is another parameter that gives you universality. So basically, if you know the VDF, one can find that velocity dispersion. So all these things have some universality in it. This we know. Okay. Now, it did not start with n-body simulations. We knew how halo formed in spherical collapse. That was already done in the early 70s. People's large scale structure book has it. The Bresch-Schechter formalism of the number of halos was there in the mid 70s. However, if you look at the structure of halo, one of the first very, very influential paper is that by Bertschinger in 1985. It is the secondary infall model. And there was also a paper before it by Fillmore and Goldreich. And it is one of the most successful analytical approaches to structure formation in dark matter halos. Okay. And what is interesting is that it has stood the test of time for 40 years. There have been some changes from simulations, but people, if you want to do analytic model, will still go back to this secondary infall. Okay. And the idea over here is that there are self-similar solutions of gravitational collapse in an omega equal to 1 universe. You can do it for a smaller omega universe. The laws will be slightly different. And it's different from primary collapse because it includes accretion of material. So outside the virial radius, there is an accretion of material, and that differs. Solutions are self-similar in nature. It's very important. And it's secondary because it involves successive infall of masses. Shells after shells fall in and form the dark matter halo. And the interesting thing is that when you solve this analytical model, you find density profiles and structures. So what about the density profile? The radial density profile sort of smoothly transits from up to the virial radius and slightly changes after that. Within the virial radius, there's a constant slope of -9/4, okay, which is steeper than the classical isothermal. And outside the virial radius, where there is this accretion, it has a slightly different slope, so it becomes a little steeper. Okay, and transition is basically at this virial or tunnel radius. Now, if I go from the simplest way in which Bertschinger did, which is a top hat collapse, you do with some slightly more BBK's initial functions, these numbers will change a bit, but not much. Okay, so it's a straight line in density. Okay, you can look at the velocities. Assumptions are very simple. Velocities are given by this. Okay. And if you look at the velocities again, up to the virial radius, it is a Paul law. Okay. And outside it flattens off a bit. So there are Paul laws in velocity and the Paul law in density. Okay. Once we have these two, Bertschinger also calculated another thing which is known as the pseudo phase space density. And this is very important. This is defined like this, which is rho by sigma cubed, and this is one of the most important and universal prediction of Bertschinger's model. It's more important because it was a fundamental diagnostic of halo structure, because it sort of closely approximates the real phase space density. So this has the same properties of the real phase space density. So you can calculate it easily from a theory or from observations. Okay. And the interesting thing is that this pseudo phase space density is also a Paul law with a fixed number, a very specific number, r to the power minus 1.875. And this extends over 2 or 3 orders of magnitude in radius, from the very center to the virial radius and beyond. Okay. Now, this is where the most important analytic model of structure formation of halos gives. 12 years after Bertshinger's paper, the NFW, the Navarro-Frenk and White results came out. Okay. And that's 28 years back, and they found that this was the density profile which I mentioned in the first slide. So there is a scale radius. So remember, the Bertshinger's model did not have a scale radius, it was just a flat line. I will show you a figure now. It has scale radius, so there's inner behavior going as r to the power minus 1, outer behavior going as r to the power minus 3. For velocities, there was an outer which was going as 1 by r, and the inner which is going as 1 by square root of r. Okay. The Bertshinger's model basically has 0 velocity anisotropy, so it's all radial in falling matter. In real simulations, it is not radial, so there is an anisotropy parameter, and the central region is only beta equal to 0, outside there is some anisotropy. Okay. But the thing to see over here is that there are new universalities, but they are different from Bertschinger. So not Apollo, there is a scale which is coming over here. So now if I look at it, you see this is the density profile. So this is the density profile, and this is the Bertschinger. The Bertschinger is a straight line, whereas this has a power law, so minus 1, minus 3. Okay, so a scale is introduced. Similarly for dispersion velocities, Bertschinger is a straight line, but for NFW halos, depending on the concentration, it goes and turns over. Okay. So in density and velocity, the simple power law relation is no more valid for dark matter simulation halos, which is what we know all the time. What happens to the pseudo phase space density? So pseudo phase space density will come from this and this, right? If I look at the pseudo phase space density from simulations, this is what they find. And this is universal across different simulations, thousands of halos. You have very similar to, so only dark matter of course, very similar, very tight relation. So if you look at this figure over here, see how much scattered the density is. Over here you see how tight the relation is. The pseudo phase space density is exactly a power law as in Bertschinger. So what has happened, the density and the velocity structures have changed from a simple analytic model to real simulations where things are falling in, accreting, going through, shells crossing and everything. But the pseudo power law, this one, the phase space, is still exactly. And this is probably due to balance of, when your density increases, the velocity also increases, things like that. But this is amazing, that it's common between both the things. And there has been a lot of comments about it. Now that was what I showed was for just n-body simulations. If you have hydro simulations, what happens? So in hydro simulations, it depends on the hydro simulations. Every hydro simulation gives a slightly different number. But the important thing is, again, there is a power law, which is not 1.875, but somewhere in 1.65 or 1.7, it's a power law. Okay. And hydro simulations basically, because of the baryons inside, there's adiabatic contraction. If you have feedback, then feedback also pushes things, but the power law is still there. Okay. So it does not matter. Whereas the density and the velocity are no more power laws with some scales, the pseudo phase space density is still a power law. So this is for hydro simulation, as you can see, still a power law. Okay. So what is the picture that has arose in the last 40 years? There's a universal single power law scaling relation across the entire halo is robust for CDM predictions, whether it's n-body or hydro. Remarkable universality consistent across halo samples, different simulations, different mass halos, okay, different redshifts, doesn't matter. And so this makes it a theoretician's favorite. One can argue that it is a fundamental property of CDM, structure formation. And so there are many, many papers which is trying to understand this match. There is no consensus. To the extent this has puzzled the theoreticians so much that there even has been a paper like this. Is it a fluke of physics? Okay. So is it just a fluke that there's a match, or there's something really, really deep inside it? Okay. So why care about this phase space density? The reason is that this has a fundamental connection to the thermodynamical properties of dark matter halo. Anything that sort of puts energy into the halo directly or indirectly will change this CDM pseudo phase space density, right? So on the other hand, it has been shown that substructure, tidal interaction, mergers, they do not change the phase space density. So if I have a self-interacting dark matter, it will add some velocity interactions, it can change the PPSD. So you can use PPSD to look at your SIDM. For warm DM, it has initial power spectra is different, so again there will be a change in the PPSD. So you can look at the change in PPSD to look at non-SIDM, non-CDM models. Okay. 40 years later, roughly last 2 years, what do we find? So give me the results straight away. For real galaxies, there is a systematic departure from Paul law. So this is if you want to construct it from observations. There's a double Paul law behavior. The baryonic influence of the galaxy extends far beyond the baryonic galaxy, and the PPSD scale free nature is broken, so be careful if you're using it to constrain non-CDM. Okay. So how do I do it? I will go very quickly through it. So we start with spark galaxies. These have high quality H1 and H alpha rotation curves of 175 galaxies in the spark catalog. This thing took a long time to do. So this was some other projects. Okay. So these are mostly disk galaxies, so they have disk in it. Choose galaxies with high quality rotation curve going up to the flat outer part. Okay, so then it brings down to 129 galaxies. Do your standard Bayesian analysis. Okay, with multi-component dark matter, visible matter models. Make sure this is not very different from what is there in simulations, like the data and mature relations. There are 2 free parameters for the visible matter, you find those. You also look at mass to light ratios. So make things which make some cuts, goes to 80 galaxies, which is a good sample. Then do something which is known as reliability cuts. I'm not going to be able to talk about reliability cuts. It's a Bayesian formalism that we sort of wrote down to say what is reliable. It is beyond best phase model selection, something called reliability, and that brings to 21 galaxies in this mass range. So this is a gold sample. On this we can find. So this is the whole sample, and from there we take out 21 galaxies. Okay. If I have densities, because from these rotation curves I can get densities. If I get densities, then from densities there's a way to go to velocities with simple assumptions of sphericity of the potential. Okay. So this is called Eddington inversion. I'm not going to go through this, but one can find the velocity distribution function. Okay. So basically I find the velocity distribution function at different radii for all these galaxies, and we can fit it very well with our own fitting function, which is much better than what Mao et al. Did in 10 years back. Yeah. Okay. So we get for all of these galaxies, we get this, and we can get the sigma from there. So give an example of these 2 galaxies. As you see, this is the data. You do this multi-model fits to the data. We get the dark matter component. From there we go the densities. For each dark matter component at different radii, we know the velocity distribution function. So for different radii, you know the sigma. You know the density, you know the sigma, we can find the Q. Okay. And this we can do for 21 galaxies. Okay. So what do we get for the PPSD, the pseudo phase space? This is the answer. Here is Bershinger's line minus 1.875, which is what the simulations also agree to mainly in body simulations. And this is what we find for the galaxies, for the gold sample of galaxies. As you go to the center, it deviates from the 1.875 line. So there is a double Paul law thing. Okay. So there are 2. So there is a slope over here and a slope over here. So if I look at carefully, so gamma 2 is the outer slope. So Bershinger and the simulations is what they get. Simulations get it like this. Real galaxy's slope is over here. And gamma 1 is the inner slope. Remember, if it's a gamma 1 also, even if you have a hydro, it did not go beyond this. So it would be around this region, but the real galaxy is so very different. Okay. So the Q is now a double Paul law. Okay, and you can find out what the different things. There's a transition radius, which goes from the outer Paul law to the inner Paul law, and a systematic departure from this. Important is a systematic departure. So the pseudo phase space density of real galaxies shows significant deviation. The classic single power law is a derivative to double power law, and this is due to the baryonic influence of the galaxy. Okay. Now let us quickly look at one galaxy. So let us look at this NGC 400, this green line. This part is RD. So this is the disk of the galaxy, the scale radius of the disk of the galaxy. After the scale radius of the disk of the galaxy, the baryons die down exponentially, and there is practically no baryons beyond this. Okay. So influence, direct influence of baryons, but you see deviation also over here, and the transition region is over here. So there is influence even after all the baryons have died. Okay. Now galaxies form in dark matter halos, you always know, and now we know that dark galaxies affect the dark matter halos. How? I can show this from this figure, this last figure. So if you look at the inner slope and look at the surface density of baryons, you can see that the inner slope is exponentially related to the surface density of baryons. Very, very tight relation. So if I have larger concentration of baryons, it will change your inner slope. And the idea is very simple. These baryons, it not only pulls this adiabatic contraction of the density, because the dark matters are moving in a combined potential of the baryons, and it's not a self-gravitating fluid, so its velocities are larger. Okay. So this is where I'm going to stop, and before I go to the next stage, this is a figure which Manush came, and just like Manush is, he came in and said, "Sir, I think it's a very important result." So I'm going to stop over here. I think it's a significant result. The single power law QR that has ruled for 40 years is no more. Shows another powerful galaxy and halo connection. This comes from simulations. And all interpretations of modification of QR at small radii due to alternative dark matter has to first account for galaxy effect. Also, all these results, are crucial for dark matter experiments. So I'll stop over here. Thank you.
Questions? Quick. Yeah.
So, for warm dark matter, why would the PPSD change? Because in warm dark matter, once the collapse starts, you will get NFW. You may not start at all if you are suppressed on small scales, but once it starts, it goes to
So
NFW.
one of the reason this, the value, exact number, that changes because in the Bertshinger's model, it starts with what top hat collapse.
In Bertshinger's model, sure,
Yeah.
but if you actually go to simulations, and you look at
So there are papers which shows that your power law, this is not a double power law, the power law has a different slope in the way warm dark matter follows, because it sort of puffs up and stuff like this. Anything basically which puffs up your dark matter halo will.
no, warm dark matter actually does not puff up your halo, because once the collapse starts,
Yeah.
that velocity is much higher than the thermal velocity of warm dark matter.
Okay.
If you take it, yeah. The other one small, how do you quantify the effect of, you said, so the Eddington inversion assumes sphericity, but we know that dark matter halos are triaxial,
Yeah.
so how would you quantify?
Okay, so this is a complete, so I can talk about this a little. Eddington inversion involves the sphericity of the potential. The density, of course, just the disk is not spherical, right? So you
Yeah.
have, disk. So what you have to construct in doing the Eddington inversion is basically you have to find spherical potential, sphericalize the potential. And with the sphericalized potential, you do the Eddington inversion. And that agrees well with, so there's a difference, a 10 to 20% difference, but that will not change this results that much.
Okay.
Yeah. This is
Any
something
other
that I
very quick
answer every time I do say this question. But
A very quick question, okay.
Yeah, my question is very similar to what Orko was asking. For the Eddington inversion, don't you assume there are no major mergers recently? It's
Yeah.
probably the same question, but
yeah, I mean,
yeah.
these galaxies, I don't think none of them has any major mergers recently.
How do you know that?
From the morphology of the galaxies, they're very stable disks. There's no, if there's a major merger, maybe like a half.
For Milky Way, only after Gaia we know that there was, only after Gaia we know that there has been a major merger, right? Otherwise it was also.
So
this was
how
not
you
this.
call a major merger is a very, so typically in structure formation, major merger is very m/2 mass. If it's like 10 times, or even Milky Way has a mass of 10 to the 12, if a 10 to the 10 goes through,
Yeah.
it will have a blip over somewhere. It doesn't, it's not a major merge. It doesn't, so it's a pseudo hydrostatic equilibrium is there always.
Thank you very much for the nice talk.
Thank you, Subha. Let's thank him again. We can go. So next speaker is Nishikant Khandai from NICER Bhubaneswar, and he will talk about dark matter halo structure.
Oh, right.
It's there on the computer. This is on, right? Okay, so I'll be following up from where Shubha has left, slightly different. So this will be talking about the structure of dark matter halos, which we think we understand very well, but we'll be talking about the how these structures or the distribution of these structures of the shape parameters evolve with time, and there'll be a lot of universal functions. So this is being the first part of the talk will be with Ayan, who is the PhD student, and these guys. And the second part and the third part of the talks will involve these hydro simulations, which we have heard about. So I'll probably stop maybe in part 2, and if time permits, I'll go to part 3. So during my PhD, Sriram was on the panel, so he used to always ask, what happens, why are you not including baryons? So I think we have heard a lot of talks where baryons do affect dark matter, and I'll show a couple of plots for Sriram there. Okay, so this is no baryons, this is just dark matter halos. This is a 10 to the 14 halo from a dark matter simulation, and this is with 2 halo finders. This is with subfind and this is with Rockstar, and then we remove out all the satellites or the substructures, and you are left with these 2 halos, which we call the central halo. So we'll be talking about only central halos because satellites may affect the way we measure the shapes of these halos. So this is another such 10 to the 14 solar mass halo, very different in shape. And what we'll be doing again is to quantify the shapes and look at the distribution over the entire simulation, the distribution function of these shapes. So why shapes? Because what's plotted here is the halo mass function, and what has been done here is that you have, let's look at the pressure vector, which is the blue line. The data is from simulation, and this is what you call the ellipsoidal collapse, that is the Shed-Torman mass function. We'll not look at talk about the Zeldovich related result. And you see that the simulations agree very well with the ellipsoidal collapse model. Okay. So look at the bias. Again, bias is also affected by whether we consider halos to be spherical or we consider them to be ellipsoidal. Okay, so this is just the definition of the mass function. On the left hand side, this is what we count. It's a histogram, and we just map it to this function, is what is plotted here. There is a definition of nu being 1 over sigma square, or nu being 1 over sigma, which is different from what Ravi uses and what generally we use. Okay, but they are the same. So we have seen that simulation suggests that mass functions are better dealt with when you are analytically dealt with when you consider ellipsoidal collapse model. And what's done here is we have listed a few of these mass functions which are universal in nature, and here is one hydro simulation, massive black 1 and massive black 2, and it goes all the way to high redshifts, okay, and the pressure sector doesn't do a good job. That's the key point here. But if I look at all the dark matter fitting functions that you look at, that you have used, these lie here, and with the hydro this is consistently down. So at smaller masses, so this is like a mass scale which has a redshift folded in. So the mass function is universal, it goes from right to left on the curve, okay, and at lower masses the hydro simulations are showing, at least this one is showing, that the abundances are suppressed consistently with whatever has been done in the literature. Okay, so it's important for looking at abundances in the context of shapes. Okay, there are some other things which I have listed out where the halo shapes are important and why one should start quantifying them a little more carefully. So looking, we have talked about clustering, 3-point function is something, and since bias is degenerate with the growing mode and sigma 8, it will affect again cosmology. Then what is the effect of baryons on halo shapes and vice versa, and how do halo shapes affect galaxy formation? So earlier halos, how do they compare with late time halos, and that will sort of dictate how galaxy grow in these halos. Okay. And then we have heard a lot of talk about dark matter interactions, and these typically may be affecting the inner profiles of halos. We have heard Shubha's talk about the velocity and the spatial structure. We also have velocity shapes, but we don't know how to interpret them, so I'm not going to talk about them right now. And then there is this nature versus nurture debate. Okay. So quick definition, we take our favorite code, the n-body code or a hydro code, we take our favorite halo finder with subhalos, a subhalo finder. We define a 3x3 shape tensor. Here xi and xj are particles I and j in the halo whose distances are with respect to the center. You have to come up with a definition of a center. And w is a weight. It can be taken to be unity, or it can be weighted with respect to the radius. Okay. So you diagonalize this 3x3 matrix, which is symmetric, and then you'll get the eigenvalues and the eigenvectors. The eigenvalues are the 3 axes, which you will talk about in the context of triaxial halos, and the eigenvectors are these directions. Okay. So one thing which we'll talk about a lot is the triaxiality parameter. So we are not interested in the absolute values of the axes, which are A, B, C ordered, but rather their ratios. And this is known as the triaxiality parameter, and basically it will determine whether an object is oblate, triaxial, or prolate. Okay. Okay. So we'll use a bunch of scale-free runs. We'll also use a bunch of lambda CTM runs. So these are the range of indices for scale-free runs, and the reason we use that is to look for self-similarity, because scale-free runs are self-similar. So we have to make sure that our simulations are doing fine. So pretty large or reasonably large runs, okay, and we go out depending on the index as to the maximum. So this is like a RNL. RNL is the scale at which sigma at that scale becomes order unity. Okay. So just the classification, this is an oblate halo. T is from 0 to 1/3, and if A is of order B and is greater than C, so it's basically like a pancake or a UFO. Okay. So this is basically the random orientation in the simulation, and here we have aligned the largest axis along the z-axis. Okay. This is triaxial, it looks slightly different, okay, and the 3 axes are ordered, and the triaxiality parameter is 1/3 to 2/3. And this is the prolate. Prolate is like a cigar, and you'll see this is like the face-on view of that, and this is the edge-on view. Okay. So this is another halo, which is prolate halo. Okay. So now what we do is to compute the shapes. We look at the Q and S, which are the ratios of B by A and C by A, and look at their distributions. And what has been plotted is as a function at every output that we have used. This is, let's just look at these two. These two are for Rockstar, these two are for Subfind. They look similar, so we can just for the time being ignore the half of the plots. Okay, this is for n is equal to 1, minus 1.3 and minus 1.5, and we are plotting the median of these distributions, okay, as a function of either m by m nonlinear or nu. Nu is in the y-axis, okay, and you see that it's a tight evolution, and it goes along some characteristic curve which we are going to quantify. Go to even more negative indices, minus 1.8, minus 2 and minus 2.2. Again you see that the curve starts flattening both in Q and S. Okay, so the question is, do these curves fall on a single universal curve? And we have done this separately for the three types, O, T, P, O being oblate, T being triaxial, P being prolate, which are denoted as orange, blue and green. Okay. So again you see for the different halotypes a characteristic curve along which these distributions or the medians of these distributions evolve. Okay. You put them together, this is for again minus 1.8 to minus 2 and 2.2, and then you see something similar. Now you put them together and you see that there is a very tight relation for all the halos for across power spectra, okay, or the power law indices, and this is all those data combined together, and we have fitted just a tan hyperbolic function on this. Okay. And you see the same thing or a similar thing, that you have universal curves separately for the different halo types. Okay. So we are not sure what's happening, why it has to be universal, but we can invoke some self-similar behavior and get with that. The reason is that the self-similarity should hold for different n's, but it seems to hold across all n's. Okay? That's the universal part of it. Okay. So go to lambda CDM. I'm not going to show all those detailed plots, just the final plot. We have a bunch of runs, okay, and ranging from 75 MPC to a GPC, and again for all the halos you start seeing something universal, and across halo types again you see something similar. There are some differences here, but we think there is a finite volume effect which is hitting us for the smaller volumes, and these are the larger volumes. So this is what we have been seeing in these simulations, that the distribution follows a universal curve, and it goes from right to left. That's the evolution part. Okay. The next thing that we can see from here is that if I look at a particular mass at a certain redshift, and I ask the question, what does the mass look at a later redshift? Okay. Because the new value will decrease with increasing for fixed mass, it will go on this direction. Okay. The mass becomes a little more rounder, okay, or the shape becomes, the object becomes more round at fixed mass. So that's something which one can infer from here. So let's look at mass functions. This is the full mass function. This is mass function by oblate, triaxial and prolate, and again you see something universal happening there. Okay. Reasonably universal, and what you see here, the oblate fractions are small, they increase with time. Triaxial fractions are much smaller, but not as small as this, but they also increase with time, and the prolate fraction decreases with time, again on one single curve. Okay. And in the QS space, you can start looking at these distributions, and you start off from here, which is yellow, redshift 3, this is lambda CDM, and you start moving along this trajectory. So that's the statement that typically halos become rounder at or more spherical at as with evolution. So this is just a short summary and questions that one would like to address in the future. Okay. So what determines the shape of halos? Is it local environment or cosmology? And what we have not done is to track individual halos through their history. So that is something which will be interesting to look at. And something which I think would be interesting is to look at these rare halos, which are the oblate halos, and how do galaxies form, or are they very different when you look at these halos. Okay. So I'll quickly, now I think I have a 1 minute, 2 minutes. Okay. So I'll move to the second part and basically start looking at a multiple expansion of these halos. We'll just expand them with YLMs. Okay. So there is a radial part and there is an angular part. Okay. And we will look at the angular profile. This is what we are going to do. And then we cannot do rho 1, rho 2, rho 3, but we can take the mod square of rho, okay, because of the inner product. And we can look at the radial part of this anisotropic profile. Okay. So this is again an oblate halo. This is what we'll call L is equal to 1, we'll call the dipole, monopole and quadrupole. Okay. So we are monopole is boring, we are not going to, it's just one color. So we are looking at dipole, and dipole is telling us that this is scaled with the monopole. So this is before rotation, this is after rotation. So this is what it looked in the dark matter only simulation. Okay. And you can see that the dipole term is weak, and basically it's telling us that it's pretty much triaxial. There is no deviation from triaxiality. We'll see another example where there will be a deviation. Okay. This is in the hydro, okay, and you'll see that actually the T value has increased. So it has become slightly more spherical. This is for a triaxial halo. Okay. Again, these are with 100,000 particles, 10 to the 13 in lambda CDM. And notice again the dipole part, and then suddenly the dipole has come in hydro. And you can see there is some sort of anisotropy, might be baryonic effects, or it can be just the halo finder doing something. Okay. And finally, the prolate halo, again very low this thing, so it's like perfect ellipsoids. Okay. And then you have again the quadrupole term. So let's just go back and stare at the quadrupole part after alignment. Okay. You'll start seeing that they get sharper based on what the orientation have chosen. Okay. So this is one way, another way of identifying which halo is oblate, prolate or triaxial. The second message that we want to take from here is that the dipole term, we have a bunch of halos and most of them have dipole terms which are 0 or very small. Okay, which means that another way of quantifying is that these halos are nearly perfect triaxial halos. Okay, there are no distortions in their triaxiality. You can invert this question and ask the other question is that one can start using this to start picking out satellites. Okay, we have only expanded up to second order. Okay, you can put in third order, remove, you can put fourth order and remove, and identify satellites both in angular coordinates and if you want in radial coordinates. So this is 3 halos. This is the monopole, this is the quadrupole, the dot dashed, and this is the dipole. Right? So dipole again in radial terms it is small. And the differences, so this is with respect to rho total. So most of it, like 80-90% of the halos profile is sort of determined by just 2 or 3 modes. Okay. So that's the message here. So I'm done, right? Okay.
Thank you. Questions?
So in the first part of your talk, so just like people worked out, universality of the halo mass function,
This is
the initial delta you can think of as sum of 3,
Yes.
lambda 1 plus lambda 2 plus
Right.
lambda 3, those will be related to the shapes.
Yes.
Can you similarly work out, like the mass function you showed for individual, yeah, exactly. Is it
Yes,
possible
so
to
I
work
think
this out?
that's, one can start asking questions about the barrier for these three kind of halos and do the excursion set for them.
Have you looked into it?
No, we just, the second thing that you should notice is that this one, this is the residual. This is between the shade torment and whatever is our fit is the largest. But shade torment does a decent job. It's not too bad.
Thank you for the very nice talk. So when you were discussing about these different multiple moments for halo as a function of radius, can you also look at SIDM halos with this, look into their internal structures, whether there
Yes,
is
so
any...
this has been integrated out to R. You can do radial thing also, right?
But
So
there
when
is
we-
a plot with, as a function of radius, right? At the
that
very end of your
is,
talk.
you are integrating over a solid angle, meaning over the entire theta phi. So one part is integrating over R and finding out what it is over solid angle, right? So this is the R part, that is the rho LMs, and the other
Oh, I
one is
see, okay.
integrating over solid angle, okay, and then finding it as a function of R, but we can do it as a function of R also, this one, right? You can integrate up to R.
Up to a certain R.
Up to
though.
R.
Yes.
Right. Pardon? Yes. So we have done that and it changes. So suddenly a dipole will appear and then go away. So that we had shown, I think, in
Yeah,
previous.
so I was wondering if you can do that exercise for SIDM.
SIDM is some interacting dark matter.
Yeah, self-interacting dark.
Self-interacting, okay. Yes, sure you can do.
Thank you.
You were looking at the triaxiality that a fixed nu, the fixed peak height. So I was wondering what happens if you actually start splitting the halos on the accretion rates or accretion histories, and if essentially maybe this universality is telling you how mergers evolve.
Right,
over
right.
time.
So that's the, yes. So we have not looked at this part, right? So that's something harder. So this is just to take a snapshot and do it. But yeah, one has to compute what is the accretion rate and even the merger history, those kind of things, you can do that.
Yes, because maybe that's what's setting
Probably,
like how halos.
Yeah.
hierarchical.
yeah.
Okay. Yeah.
So under what, will they go through cycles of OTP or not, that we don't know, right?
Have the next talk, I guess.
Really, I don't know if I missed. Does your halo have substructure? Did you
Has,
talk about
but-
the alignments?
Pardon?
Did you talk about their alignments?
Yes,
and
yes,
so on?
but substructures, we have removed the substructures, we are only looking at centrals. So all, yeah.
Let's thank Nishi again. Next talk is by Susmita Adhikari. It's on dark matter constraints using galactic structure.
All right, it's nice to see everyone here. So today I should also thank the organizers for letting me give a talk. All right. So yeah, so I'll be talking about how we can constrain dark matter properties from the inner structures of dark matter halos. So we've heard a lot of introduction about what dark matter halos are, and essentially we are currently at a stage where there are multiple lines of evidence about the existence of dark matter. Right from the beginning, from rotation curves to to virialized clusters, to galaxies and clusters, to the existence of disks, and in more recent times, the CMB, the large-scale structure, strong lensing bullet cluster. So we have various, so it's a really robust model, and moving away from it will take significant effort. So while we now understand that a universe, the matter component of the universe has to be largely dominated by this dark component, because this dark component gravitates, and we expect the largest overdensities of dark matter to exist in these structures that we've been talking about in this session, particularly called dark matter halos. So dark matter halos are basically endpoints of structure formation, and they are the potential wells within which all of the galaxy formation takes place. So that's the standard model of galaxy formation and structure formation that we think about. So dark matter halos have been studied quite extensively through n-body simulations, particularly the standard paradigm, right, which has been very successful in explaining the large-scale structure of the universe. The standard paradigm of having cold, collisionless, cold, non-relativistic collisionless dark matter has been tested quite well and has been studied quite extensively. So even in the standard cold dark matter scenario, where by cold we mean that dark matter does not have significant thermal velocity, its bulk velocity dominates any thermal velocities. The inner structures of dark matter halos can have very rich phenomenology, as we've been studying. We understand that the structures of these dark matter halos, particularly as studied through simulations, have show universal behavior. We also understand that in the cold dark matter universe, where structure is seeded through perturbations, you expect to have the smallest overdensities collapse into gravitational nonlinear structures. So you expect hierarchical structure formation. So each of these dark matter halos have hierarchy of smaller substructures within them. But over time, this structure of dark matter halo we also understand now in more detail, even when we want to test out completely the cold dark matter paradigm, there are actually many even more beautiful things that we can really start to study when we start studying the inner structures of these dark matter halos. For example, we have this idea that dark matter halos, so this is the density profile of a dark matter halo, this is the slope, the density, a logarithmic density slope as a function of radius, and we expect it to be most halos to look like NFW, where it goes to -1 in the inner region, and the logarithmic fall off hits -3, which is this profile over here, dot dash. But now we understand that particularly near the outer regions of the halo, there is actually a significant departure from this behavior, and all of these different behavior are actually sourced and can be seen beautifully when you go ahead and look into the phase space structure. If you see the velocity and the radius structure of dark matter halos, you start to see many more different structures, which you can actually go out and try to test in the universe. All right, so I will not talk about particularly the cold dark matter scenario. I will talk about, or rather I will not focus on these specific structures today. What I want to really talk about is how, while on large scales, cold dark matter has been a very successful model to explain the clustering of galaxies on large scales. On smaller scales, when we really go and test these regions of high overdensity of dark matter, there have been some significant challenges to this cold dark matter scenario, right? And these challenges have come up from observations, with our observations getting really, really sophisticated over the past few decades, right? Some of which is, of course, these are well known and I'll just state them, and over the past 2 decades, many of these have evolved. So the standard issues that we talk about are of course the core cusp problem. When people went out and measured the stellar velocity profiles of dwarf galaxies, they saw that most of these dwarf galaxies, instead of having a cusp, right, where you expect the dark matter to steepen towards the inner regions of the halo to a -1 NFW-like slope, most of these dwarf galaxies show a shallower, most of the classical dwarf galaxies show a shallower core region. Other than that, we went and counted the satellites, the satellite galaxies of our Milky Way, which we think live inside, their own dark matter halos and are substructure in the larger Milky Way halo. We found that there was a large missing satellite problem, that CDM theory, cold dark matter theory, predicted many more satellites compared to what we were observing in the universe. And then there was also the too big to fail problem, essentially that the brightest satellites that you saw in the universe, if we imagine that they should be living in the most massive satellites of CDM halos, they should have had much larger circular velocities. So somehow the largest circular velocity halos in CDM simulations don't seem to be hosting galaxies. So that's the too big to fail problem. So these problems have existed for a while. They have now been reframed, I would say, rather than Firstly, I'll just go into what is the new framing of some of these old problems. So it's like a status update. So essentially what is happening is this, the missing satellite problem to start with is no longer considered a tension anymore. And this has largely been attributed to better observations, finding fainter galaxies in the Milky Way. And as a matter of census, it appears that we don't have, just if we were to count the numbers of galaxies, it appears that at least in the Milky Way, we don't appear to have this missing satellite problem anymore. The core cusp problem, now that we can measure not only a handful of classical dwarfs, we can actually measure a large tens and 50 or 60 dwarfs going to fainter and fainter regime. The core cusp problem has also been recast to a large extent. In fact, now we don't only see cores in galaxy, satellite galaxy halos, we actually see a diversity of rotation curves. Okay, so the scatter, so the entire spread of rotation curves of galaxies from dwarf satellites and nearby galaxies is much larger, is still significantly larger than what we actually expect in CDM. So the core cusp problem one can think of has been transferred into this diversity of rotation curve problem. And finally, I think even though the census of number of galaxies is more or less resolved, I think the relationship of how stars populate dark matter halos is still not well understood. Okay, so the stellar mass halo mass relationship, the relationship of star formation rate to these faint satellite galaxies or halos is still not a solved problem. We still don't completely understand how to go from a CDM universe to explain the stellar mass halo mass relation or the diversity of rotation curves that we see in the real universe. Okay, so particularly a lot of these problems were, a lot of these classical problems had motivated models of dark matter that essentially in some sense tended to suppress structure formation, suppress clustering in some sense, right? So in particular, we think that there's a potential well, CDM being non-relativistic and cold would just collapse into these potential wells. But if CDM had a lighter mass, had thermal velocities, or if these CDM particles had other ways of exchanging energies, these bulk flows would then we could be able to disperse out dark matter particles from these deep potential wells, creating essentially shallower halos in shallower cores, or disrupting away satellites essentially, right? We wouldn't collapse to the smallest objects. So while these were original motivations for thinking of many of these models, we actually, going ahead, while some of these motivations have been recast, I think it's still interesting to go ahead and ask, what do these dark matter structure, the internal structures of dark matter halos actually, what kind of constraints do they put in the different do they put on the particle properties of dark matter, right? So we can we can still go and ask just from motivation from particle physics side, like how do these profiles actually constrain the different properties of particle dark matter or wave dark matter. All right, so I have particularly with collaborators been working quite extensively on self-interacting dark matters. So unlike in cold dark matter, where dark matter can only interact gravitationally, self-interacting dark matter are essentially dark matter particles that are allowed to have some interactions with themselves beyond gravity, right? So what this essentially does is, because the particles can interact with each other, it gives them a channel to exchange momentum. It gives them an additional channel to exchange momentum with each other. So it can redistribute the energy of the particles, and therefore it predicts significantly different internal structure, the dynamics of dark matter particles in these dense regions have significantly produced significantly different structures. So mostly we understand that self-interacting dark matter tend to form cores at the center of halos. And this is particularly because if you have an NFW-like CDM halo, or if you have dark matter gravitationally bound structure, the internal velocity structure looks something like this black line. And what self-interaction does is transfers heat from this hotter region to the inner cold regions of the dark matter halo. So that essentially tells you that it heats up the inner regions of the halo, basically allowing particles to escape from the inner core of the halo. So not only does it escape from the inner core of the halo, it also makes the profile steeper in the outer region. While this was the standard picture, we also understand that while coring is the first phase of dark matter evolution in the self-interacting halos, what actually happens is, if you allow for self-interaction, and if you allow for large enough self-interaction, after the stage of thermalization of the halo, if you have too many self-interactions, these halos actually eventually tend to evolve to, I'm doing really bad on time, tend to evolve to core collapse structures. So what essentially happens is that once you thermalize the inner part of the halo, and because of this thermalization, if the hottest particles tend to escape, the core actually tends to collapse to reaffirm virialization. So it's a negative heat capacity problem in gravity. And as the core shrinks to a smaller radius, it then settles down to a wider velocity distribution, hence losing even more hotter particles, and eventually this becomes a catastrophic process leading to the collapse of the halo core. Okay? So essentially what happens is it's a competition between two time scales, your local dynamical time scale to the interaction time scale. So all self-interacting dark matter halos are in fact expected to core collapse at some point of time. So you form a core initially, but eventually if you have too many interactions per orbit, you actually start to become much steeper than even the NFW profile. So you expect a core forming phase, and then you eventually go into this core collapse phase. So essentially, what was well known is that while this has been known that SIDM halos should core collapse, typically the time scales for core collapse have been much larger than Hubble time, given the densities of dark matter that we expect in the universe. However, recently it's been pointed out that in tidal environments, if you have satellites of satellites of large galaxies, the outer part of the halo becomes colder because of tidal stripping. You can actually start the opposite transfer of heat much faster, and you can really start to core collapse in cosmological timescales. Not only do you have this when you have elastic interactions, this additional channel of heat loss is even important if you move away from elastic scattering, like I'll take 2 minutes, situations, and move it to dissipative dark matter self-interactions. Then also you start to core collapse. So right. So basically, the distribution of dark matter in halos encodes various types of, a rich phenomenology of structure inside of it, right? Whether you're forming core, cusps, collapse, you can, where your cores or your cusp or your collapse, these different stages of halo evolution can be tested by a variety of observations that we can look into. I'll just take 2 extra minutes. Where are we right now? So this is the typical expectation for elastic scattering. So on the x-axis here is the interaction cross-section times v, and this is the velocity scale, so the halo mass scale. So typically on cluster mass scales, the most robust constraints are these bullet cluster constraints, which are of the order of 1 to 2 centimeters square per gram. And on the dwarf scales, you can essentially have much higher cross sections. In particular, what we've been working on there are various intriguing observations that hint at something strange happening on both the inner, particularly in the dwarf scales, which I will not go into depth. In particular, people are now, instead of finding core cusp halos, there's been an evidence of finding a substructure in a strong lens system, which is about almost 4 sigma away from an expected subhalo in a CDM universe. What we have been working on recently is on cluster scales. Can we put better constraints on the dark matter self-interactions on these massive cluster scales? So in particular, most of the cluster studies have been focused on measuring the cores of dark matter halos, right? The sizes of the cores. But if you look at a galaxy cluster, this is a 2 megaparsec size, roughly galaxy cluster. The studies that test SIDM are basically strong lensing studies that are measuring the dark matter mass in these regions. And of course, in these regions, there's a massive galaxy sitting over there. So a lot of the very stringent constraints that come on cluster scales are thought to be contaminated by these massive galaxies sitting there. But what we have been looking at recently are these galaxy clusters and trying to understand whether we can get constraints on these dark matter particles from the entire profile of the dark matter halo. So we've been measuring these dark matter distributions from weak gravitational lensing in galaxy clusters. And essentially, while the strong lensing probes this part, weak gravitational lensing, which measures this excess surface density, probes a much larger region of the dark matter halo. So what we've been finding essentially is that there are some subtle discrepancies from a CDM expectation, which is this black dashed line over here, particularly in the inner parts of the halo. So we've been using these slope profiles to constrain dark matter density distribution. Given how good weak lensing measurements are today, we are essentially trying to use these measurements to distinguish between different dark matter models. So what we are really trying to measure is this region. So we have some part of the core in the outer regions of the dark matter SIDM core, but we are also seeing this steepening over here, and our weak lensing studies are becoming so accurate now that essentially we can, while the matter is pushed out of the core and it accumulates here in the outer region, current lensing surveys can really start to distinguish between these models. So in a recent study, what we've been doing is we've been using these lensing profiles and comparing these models to these dark matter only, to these SIDM self-interacting dark matter simulations. And for the first time, we've used the entire profile of the dark matter halo, starting from the scale radius to the virial radius, to put constraints on the self-interacting elastic dark matter interaction cross-section. And our constraints are competitive with the bullet cluster constraints currently, which is of the order of less than 1 centimeter square per gram. And we've also gone ahead and actually, instead of elastic scattering, if you had dissipative scattering, you would actually start to make the profile much steeper than CDM. So you could also start putting constraints on these dissipative dark matter core collapsed models, even on cluster scales, using the entire profile of the halo from the scale radius to the virial radius. So we use these measurements to put some novel constraints on these dissipative dark matter models. And while currently, even with DES year 3 data, our models are already competitive with a bullet cluster-like constraint. With a survey like LSST, our current constraints just from the outer part of the halo, outside of 0.2 megaparsec, which is at the edge of the core of the SIDM, if these are our current constraints, with a survey like LSST, our constraints will become really, really strong. So I'll finish essentially with that essentially, given a vast range of phenomenology which is now being looked into, and the power of current data, we can really start to be creative about what are the different ways in which we can test dark matter. And I just wanted to talk about this small work where we have used not just focused on the core, but essentially the entire structure of the dark matter halo to put some first constraints on these cross sections. Thank you. I'll stop.
A very quick, only one question. Another person, just start.
So my question is that these self interactions, repulsive or attractive doesn't matter. It's depends only on that cross section. Is it true?
Yes. So we don't go into the microphysics. So essentially, yeah, it only depends on the cross section and how much energy you.
So another quick question is that, so in this type of self-interacting models, so you only considered these elastic scatterings, but there can be some 3 to 2 scattering that 2 dark matter can go to 3 to 2. 3 to 2 processes can occur. So in that case, how these results change?
Yeah.
Do you have any
So I've
idea?
spoken about both elastic scattering and these kind of dissipative scattering, where you might have 2 different dark matter microstates that are slightly separated in mass, and you can actually lose net energy.
So I am actually talking about the single component.
Okay.
Seemed like that where this 3 to 2 process happens.
I see. You can tell me about it. The microphysics of it, you can tell me about it later. Okay, thank you.
Thanks.
Next speaker is Vikhyat Sharma. He's going to talk about LIMR cosmology.
I hope I am audible. Welcome to the last talk of this session. I know it's time for coffee, but I already thank you for being patient and sitting here. So, hi, I am Vikhyat Sharma. I am a 4th year PhD student working with Dr. Orko Banerjee at IISER Pune. The topic of my current project is N-body simulations for LIMR cosmology. I will start with a brief motivation to the topic. As everyone in the room knows that more than 80 to 85% of the matter in our universe is made up of something which we very feebly understand. We call it dark matter. Now there are different models of what this dark matter could be. It could be some cold dark matter particle, it could be some hot dark matter particle, there might be some ultralight dark matter species, or there can also be some self interaction within these dark matter particles, or it can be something else that no one of us has thought of yet. But as we know from the standard model that there exist a number of species for the baryonic part of the universe, similarly there is no reason to assume that all the dark sector has to be made up of only one kind of particle. So we assume a scenario where you have although there are theoretical reasons to assume that majority of the dark matter has to be made up of cold dark matter. So we consider a scenario where CDM is still the dominant part of the total matter density in the universe, but you also have another species which is a light species. So there is a group of particles which people have termed recently as LIMRs. LIMR stands for light but massive relics. So these particles being of the order of, so their mass is of the order of a few electron volts. So these particles act like hot dark matter species, and being very light, they would show up in as a change in delta N effective value at the CMB, because they are relativistic. The significant part of them is relativistic at the CMB, and then they would become non-relativistic at late times and will add to the structure formation today. Now people have tried to put constraint on properties of these LIMR particles, but no one has explored the full non-linear regime. There have been studies on the linear scales. Now we want to use N-body simulations to explore the complete non-linear regime. Now let me tell you what the methodology previous to this work exists. So to run an N-body simulation, This is a way. So you start with class. I think class needs no introduction in this community. And then there is a code called reps, which is scaled for rescaled power spectrum. So when you want to run, when you want to set up the initial condition for a massive neutrino cosmology, if you directly start with class and then run n-body simulations, you will face some discrepancies. So reps modifies classes power spectrum at initial redshift. In our case, we choose it to be 99, and sets up the initial condition to run a massive neutrino simulation. And then we have ENGINE-IC, which comes up with the gadget. So what ENGINE-IC does is it takes the initial power spectrum from reps and then sets up the initial particle position and velocities in a simulation box, and then gadget runs the n-body simulation. Now this pipeline already works for a scenario when you have only CDM and CDM with massive neutrinos. We want to modify it to a scenario where this pipeline works for a 3-fluid scenario. By 3-fluid I mean you have CDM particle, standard model neutrinos, and these third species of LIMR particles. That is what we want to do. So for doing that, the plan is we first will have to modify reps to set up the initial condition for a 3-fluid case. Then we would have to modify ENGINE-IC to again for a 3-fluid scenario, and then we will have to modify gadget. Now we start with the taking inspiration from reps so reps solves the fluid equations for doing the backscaling on the classes power spectrum. So these are a set of continuity and Euler equation for CDM and neutrino particles. We assume baryons to be pressureless for our case. And then we also set up the equation for LIMR particles similarly to that of neutrinos, apart from the difference that they would have a different free streaming scale apart from the neutrino particles. And when then we close this set of equation with the Poisson equation. We consider these normalizations and solve the set of equation that I showed on the previous slide. The point to note is that these existence of these LIMR species will change the growth rates of CDM as well as the neutrino particles. Now before going to the results, I would like to show you some checks that we had to do on the 3-fluid pipeline. So if you remember, the first point was to modify reps. So we write a code called pyreps. Reps was originally written in C, pyreps is written in Python, hence the name pyreps. So the pyreps is capable of running setting up the initial condition for a 3-fluid scenario, but before running it for a 3-fluid case, we should check it for a 1-fluid and 2-fluid against reps, so that we know that the code is working fine. These results show exactly that, and the result between reps and pyreps match within the machine precision. Pyreps is now a publicly available code. You can scan this QR for the GitHub page, and then pyreps is done. So my modification to reps is done. Next step is to modify ENGINE-IC. Now a perfect check to see if ENGINE-IC is working fine or not is, so what ENGINE-IC does is it takes the power spectrum, sets up the initial particles, position and velocities. Now from that box of initial particles, you read density field, generate the power spectrum. Now the power spectrum thus generated should match with the power spectrum you fed it with, and that is what exactly this plot shows. So ENGINE-IC is also done. This also works. Now the next step would be to modify gadget. We do that, and now we have the complete pipeline. Here is a final check before running, showing you the final results. Consider these two scenarios. In one case you have a CDM particle and 3 neutrino species. In other case you have a CDM particle and 2 neutrinos and a third LIMR particle. These are initial conditions at 99. You pass it through the pipeline that we had just set up, and you get the results at redshift 0. Now if you consider that this LIMR particle is a neutrino, then the scenario would be, in one case you have a CDM particle with 3 neutrinos, in other case you have a CDM particle, 2 neutrinos and the third neutrino is passed with the LIMR flag. In principle these two scenarios are same. Now the results should match if the pipeline is working correct. These are the results where you see that both at redshift of 99 and at redshift of 0 we are able to match the results, hence the pipeline is working fine. Now I will show you the results. Before showing you some quantitative results, I would like to show you qualitatively how the structure formation is structure is washed out due to the presence of these LIMR particles. So in this video, In this video, you can see for the first case where I have only CDM particle, here CDM with standard model neutrinos, and in this case we have all the three species. And if you cannot notice, then I also have the zoomed in picture for you. So this is the only CDM case, this is 2 fluid CDM plus standard model neutrinos, and this is a 3 fluid case. And this box has been zoomed in on the lower panel. One can see that as you include standard model neutrinos and LIMRs further, the structure is washed out. Now if you look at the individual clustering of these particles, CDM clusters the most, of course. Neutrinos have very less clustering, and LIMRs have clustering somewhere like much more than neutrinos, but still less than the CDM, which is expected. Now I will show you some results. So we choose the LIMR particle to be a Dirac fermion in the first case, and then we produce the power spectrum. So here you can see the power spectrum of only CDM case, CDM along with neutrino, standard model neutrino case, and the following is what I will follow in the next plots also. We do two things. First, we keep temperature of the LIMR particle fixed and vary mass of the LIMR particle. In other case, we keep mass of the LIMR particle fixed and vary temperature. One can see that suppression is more when you increase the mass of LIMR particle, which is expected, and here you can see that as you increase the temperature of the LIMR particle, the suppression is more. So this is for the power spectrum. Then we go on and look at the halo mass function. Halo mass function is defines how number density of halos would change with mass of the halo in the simulation box, and we also see the suppression here in the similar manner as we saw for the power spectrum. One thing to note for the halo mass function is, so to produce the halo catalog, we use code called Rockstar. Now Rockstar is only sensitive to the type 1 particle, which means that contribution from standard model neutrinos and the LIMR particles has not been considered in this case. So these are comparison between only CDM halo mass functions for different scenarios. Then we go on and look at the mass concentration relation between halos. So mass concentration relation is defined as the ratio of virial radius with the scale radius. Qualitatively, it tells you how centrally peaked the density profile of a dark matter halo is. So we also in this case also the contribution from the other two species has not been taken into account. These are only CDM comparisons, and trends are as expected. For low mass halo you have higher concentration, for high mass halo you have lower concentration, which is expected. And then we go on and calculate weak lensing. Now to calculate weak lensing in a simulation box, we calculate something called excess surface mass density. Now excess surface mass density is calculated as this quantity, and here in this case we take into account the contribution from all the three particles, and then we add the weak lensing signal in all the three cases. The trends are as expected in that case. Now one thing to note in all the plots is that the power spectrum of all the observables are more sensitive to the temperature as compared to the mass, and that is what we expect, because the things are more sensitive when you change temperature. And then we go on and look at instead, so in the previous case we had considered a fermionic species for the LIMR particle. We also go on and consider LIMR to be a boson. We change the distribution function while setting up their velocities, and we again calculate all the 4 things that we had calculated: power spectrum, halo mass function, concentration, and weak lensing. So I will not go into the details. The trends are similar to what we had for a fermionic species. And so these are the first results from n-body simulation of 3 fluids evolving non-linearly, fully non-linearly. Now these are the very first results, and there are a lot of things to explore. For the current work we had only thermal LIMRs. We also want to look at how non-thermal LIMRs would evolve. Then we also want to look at if the thermal velocities of these velocities of these LIMR particles might have some other distributions. They might follow Fermi-Dirac or boson that we had checked. they might also follow some other different kind of distribution. We also want to check that, and we also want to we plan to look at how varying free streaming scales and delta ineffective value of these for these LIMR particles would change things. These are some references, and thank you for being patient.
Thank you very much. It's very exactly on time. Yeah. Questions?
I have two very naive questions. First of all, as you have seen, you have also seen in your simulations that if you introduce a light dark matter, then the structure starts to wash out, right? So my question is, how much the fraction of dark matter, so maximally it has to be cold dark matter. So what is the fraction of hot dark matter that you can introduce so that you are still okay with the structure formation?
Okay, so so these are the first checks. We have not been sensitive to what percentage of the matter you can give it to these LIMR species. That will be constrained once we compare it to the observation. But for now, these are subdominant part of the matter only. They only contribute to a few percentage of the total omega m.
Okay.
Yeah.
And the other thing is that how different it is from dark radiation. So people often talk about dark radiations in the.
So these particles at CMB would contribute to dark radiation in the sense that they would have a non-zero delta ineffective value.
Yes.
But at late times, due to their massiveness, late time somewhere between CMB and today, they would become non-relativistic and then start contributing to the large-scale structure formation.
Okay.
Yeah.
Thank you.
Hi, Vikyat. Thanks for a nice talk. I'm just curious about one thing. You said Dirac fermions. Where
Yes.
does the Dirac-ness nature come in? If I do it for Majorana fermions, it should be the same, right?
Okay, so if you change the what you call G value for the species,
yes,
that value is highly sensitive to the value of delta ineffective that you will have. And when you calculate the omega, which is the contribution of these particles in the omega matter, that is also sensitive to that G value. So G value is different for Majorana and Dirac. So that is why I said that we have chosen Dirac.
Okay.
Yes,
Thank
because
you.
that is sensitive to those two.
Thanks very much for the nice talk. Thanks.
Any other question? Any quick question? No? Okay. Okay, let's thank all the speakers of this session. Yeah. And we'll have a break for 15 to 20 minutes. Yeah.